Hey everybody, 24.1 here, talking specifically waves and sound. And really, we focus on just kind of waves and what periodic motion really is. That's kind of what we are focusing on in this section. So, what the first thing that we're going to do, if we're going to learn about kind of what this harmonic motion is and repeated motion, we got to make sure that we understand the difference between linear versus harmonic. Okay, so linear motion would be like your typical how you're going someplace. I'm going from here to there, right? I'm going to go for a run. I'm running from this spot to this spot, or I'm sliding down a hill. I'm going to go from the top of the hill to the bottom of the hill. Linear motion doesn't mean it has to be a straight line, but you're going from point A to point B, right? Harmonic motion is going to be something that repeats itself over time. We just set up a swing set for my kids, and Merrick just wants me to push him in a swing over and over. And that would be an example of a harmonic motion. I push him once, and he keeps going for a little while, right? Now, we're going to focus on that harmonic motion. And a pendulum is one example of that. So a pendulum is just a device that swings back and forth. And we're going to use a pendulum to learn about a lot of this vocab. So in this section, there's a ton of vocab. There's like 12 vocab words in this section. That would be a great way for you to really kind of take your notes. 12 vocab words is a lot. And this section is really just a lot of vocab. So as I'm going through the notes, you'll see all of the blue underline. Those are all the vocab terms. Make sure that you have them, okay? Because they are all good. They're all important vocab terms, and they're kind of the foundation for this chapter 24. So a pendulum is a device that swings back and forth. You guys have seen them like sitting on a swing, or the pendulum in like a grandfather clock, right? Those are all pendulums. They're devices that swing back and forth. Great. Now, a cycle is one unit of that, one unit of harmonic motion. So if we are talking about a swing or this pendulum, you can see in the picture, we're going to start our pendulum up on this side. As it swings down, it goes to the middle, and it's going to the other side. Now, is that one unit of harmonic motion? Is that one unit where it starts to repeat itself? Not technically, because it has not gotten back to where it started yet. Okay, it's gone one way and now it needs to go back to the other side here, right? So it starts going back down and up top. Once it gets back there, now that motion starts to repeat itself. Notice how the motion here on this ending slide is going to be this is basically the same picture as over here, just with begin next cycle, right? So that it would be that motion that repeats itself. So that would be one cycle, okay? One unit of that harmonic motion. Harmonic motion can be fast or slow, but speed is constantly changing during its cycle. So if you think about a pendulum, there's going to be points in that pendulum, or if you're thinking about you on a swing, there's points when you're on that swing where you are moving faster and slower, right? You're not actually moving the same speed the whole time. Your speed on that is different. Um, you're going to be going, for example, as you move up in that swing, you're starting to slow down, right? And then you come back down, and now you're starting to speed back up. Your fastest point is going to be at the very bottom, and then you start to slow down as you go back up to the other side and speed up as you go down, right? So your speed is constantly changing in that example of a pendulum, okay? And we're going to use some terms period and frequency to describe the rate of cycle. So period is the time it takes for one cycle to occur. If you're sitting on a swing, you can say, okay, I'm going to start my timer and stop my timer when they come back to where they started. That is one period, the time it takes for one cycle. When we're talking about a swing, that's pretty easy to think of. When we're talking about vibrations of a guitar string, the period is very, 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 very small, right? The amount of seconds per one cycle is tiny. So period is the time it takes for one cycle to occur. Frequency is the exact opposite. Frequency is the number of complete cycles per second. So how many times you go back and forth per second. If you're talking about a swing, you're probably going from one side to the next and back. It probably takes longer than a second, right? So your frequency, the number of complete cycles per second, is actually going to be less than one, because you're not actually, in 1 second, you're not actually making a full cycle, right? Versus a guitar string, you can see in this picture, a guitar's A string vibrates at 220 hertz. That means that it vibrates 220 times per second that is its frequency. So 220 cycles per second. Frequency would be cycles per second. We measure frequency in hertz. You guys have probably heard that before. Let's see. Next up, solving problems. So here's your equation for period and frequency. I would write this down. I do have one question in your review questions that kind of asks you to take a look at this, and you'll have to do this tomorrow as well. But period is just the 1 divided by the frequency, while frequency is 1 divided by your period. All right, amplitude is the next one. Amplitude is kind of just like it sounds. If you're going to talk like if something is like a high amplitude, whatever, it means big, right? So the amplitude is the maximum distance the oscillator moves away from its equilibrium position. So in this situation, here's our pendulum. We're back. This case, it's just moving a little ways, right? Here's the equilibrium is going to be the center. Equilibrium is where it would be at rest. If we're talking about waves in water, equilibrium would be like water level, sea level. Okay. A small amplitude is when it doesn't move very far away from that, right? A larger amplitude is when it moves quite a ways away from that. Okay. So amplitude, small amplitude, large amplitude, equilibrium is an important term there. Remember, equilibrium is the point at which it would be at rest. Now, again, amplitude of the water wave, I kind of just mentioned that, but amplitude of the water wave, it's not the highest point to the lowest point like we might think. Remember, it's the distance from equilibrium. And equilibrium is that water level. So water level would actually be right in the middle of that. So we're going to take the highest point to the lowest point. Our amplitude is half of that. Okay, so that's what amplitude is on waves in water. A pendulum with an amplitude of 20 degrees swings 20 degrees away from the center in either direction. So we may measure amplitude in a distance, like this wave is 1 meter in amplitude, or we may say that the amplitude is 20 degrees from equilibrium. Okay, we use degrees when we're going like with a pendulum where it's angles. We're going to use distance when we're talking about like waves in water or something like that, where we're dealing with height of a wave. Now, in a perfect world for me, I could just give my son one push on the swing and then he would just keep going for forever, right? I was just pushing him last night and he would have me push him a little bit and then he'd tell me I'm done. And then about 10 seconds later, I needed to come back, probably less than 10 seconds, probably about 3 seconds later, he needed me to push him again. And then he very quickly told me I was done because he doesn't want to get too high. He's kind of a scaredy cat like that. So friction slows a pendulum down. We want that swing to go for forever, and it would. Objects in motion want to stay in motion. The reason it doesn't is not because of gravity, it's because of friction. Friction slows it down. Gravity works to pull it down, yeah, but as it's pulling it down, it's speeding up so it can go right back. The energy you put in will stay there, right? Friction is what is slowing it down. It's converting that energy of motion into heat energy, really. And that gradual loss of amplitude, so that like as you're going, as you're swinging, you start to get lower and lower. That is called damping. For some reason, this term damping is very often forgotten. Usually when we take our test, this is one of like, I don't understand why people don't remember this one. It's just a vocab word, but damping is very often forgotten, and it is the gradual loss of amplitude. We all know it. We all have seen it. You know that you can't just give one push on a swing and it will go for forever. It doesn't work that way. It's going to slow down, and the term for that is damping. Okay, and here this picture just kind of illustrates it. Here we start with a really long amplitude, and after 1 minute, it's lower. After 2 minutes, it's lower. After 3 minutes, hardly moving at all, right? Now, graphing this harmonic motion, I am willing to bet that you're going to be doing a lot more of this as you take physics and things like that. We don't spend a ton of time graphing harmonic motion, but we do want to kind of know some of the big points, and we're going to hit that a lot more next section. 24.2 does a lot more with the graphing and understanding all the different parts of the harmonic motion graph. But a graph is a great way to show harmonic motion because as you can see, we see a position change as time goes, and we can see that it is repeating itself, right? We can see that motion is the same over and over and over again. Let's see, next up, harmonic motion graphs. Again, like I said, we're going to talk a lot more about this tomorrow, or not tomorrow, but in section 24.2, we'll talk a lot more about it. I'm just going to show you the big things here. Hey, 0 would be my equilibrium, right? When I'm up, that's a positive amplitude. When I'm down, that's a negative amplitude. Notice that the amplitude goes 20 centimeters above or 20 centimeters below for a total amplitude of 20 centimeters, right? Take 20 to negative 20, that's 40 divided by 2. The period, the time it takes for one cycle, well, I just have to find on here one cycle. Where does it start to repeat itself? In this case, it's up high in the positive right here. It goes down to the negative and back up high to the positive. That would be one cycle. That's one unit of harmonic motion. That's one area where it starts to repeat itself. And the time it takes to do that is what I have for my period. And if you guys remember back to those equations, if we want to solve for frequency, we just take 1 divided by the period. So if I want to know how many hertz that is, I just take 1 divided by my 1.5 seconds. And that's what I would use to find my number of hertz. Now, natural frequency is the frequency at which a system naturally oscillates. So it's going to go back and forth at this rate all the time. A guitar string, you can pluck that guitar string and you know what frequency it will be at all the time. It doesn't matter how hard you strum or anything like that. That is its natural frequency. It will play that note. It's going to have that many hertz, 220 hertz, for that A string on a guitar. So the natural frequency is the frequency at which it naturally oscillates, and every system that oscillates has a natural frequency. Okay? The swings on my swing set, they will oscillate with this natural frequency. It doesn't matter how high I push my son, okay? It's going to take him the same amount of time to do that. He's going to do the same number of reps per second as he would whether it's a big push or a small push. He's going to go the same number of cycles per second. And that's what the natural frequency is. And we can change that natural frequency. If you think about a guitar string, how do we change the natural frequency? Well, you see him there tightening or loosening that guitar string, and that changes the string length that he's using. You can also use your fingers, right, to change the length of that string, and that can change that frequency. It can change the note that you're actually playing. Okay? If I'm on my swing set, I probably want to change the height of the swing. The lower the swing, the longer it's going to take. The shorter, the higher up the swing, the faster it will go back and forth. And that's that natural frequency. Every system has a natural frequency. It has a system frequency that it wants to oscillate at naturally, but we can manipulate that by changing the length of the string. So you can get a swing moving by pushing it at the right time every cycle, right? So if I'm pushing my son, it doesn't work to push him when he's on his way down towards me, right? A push at the wrong time doesn't help. But if I apply a periodic force, a force that is repeated over and over at the right time, a force that goes with my natural frequency, then you guys know what happens. You can swing higher and higher, right? And that is called resonance. Okay? When I'm applying that force over and over at the right time, I may get an increase in amplitude. And that's what resonance is. Resonance is an increase in amplitude resulting from a periodic force that has the same frequency as the natural frequency. So when I'm pushing my son on the swing and I keep pushing and pushing and pushing, he gets higher and higher and higher, right? His amplitude increases. And that's what this graph shows. Okay? We push right here, goes down, and comes back up, and we push again and it goes down and comes back up, and we push again and it goes down, right? So as long as we apply that push at the right time, the same time every cycle, that periodic force, the force matches the natural frequency, we may get an increase in amplitude, which is called resonance. And that is it for your 24.1 notes. Thank you all so much.